So what we want to look at in this set of notes is motion in one dimension. So in order for us to first think about motion in one dimension, we need to just review the idea of reference frames. So what you can think about when we're looking at reference frames is you can imagine that you have car 1 here. This is car 1 and here's car 2. So let's say car 1 was moving at, let's say, 25 miles an hour. And car 2 is moving at 30 miles per hour. So car 2 at some point overtook car 1 and passed it. And you're sitting here, this is you, you're sitting here on the side of the road watching the green car pass the red car. Now to you, what you see is you see the green car going 30 and the red car going 25. But what the person in the red car sees, the person in the red car sees the red car, they see the green go 15. They go 5 miles per hour as it passes them, because the red car has a moving reference frame, and so they have to measure everything against their moving reference frame. So the red car only sees the green car passing at 5 miles an hour because that's the difference between them. So we just need to remember that whenever you're moving, you have to account for your reference frame. So your measurements are based on what frame of reference you measure from. And so whenever we're going to measure, usually what we'll do is we'll pick some reference frame that isn't moving. So let's say that because you as the person are sitting here on the earth, you're in a reference frame that isn't moving, and then you would measure everything against some point that isn't moving. And then what we would say is, oh, car 1, that's why we could say car 1 was going 25 miles per hour, because they're going 25 miles an hour against the earth, which is not a moving reference frame for the general purposes. Yeah, it's going through space and all those other things, but for every object on the earth is seen as a non-moving frame for the basis of what we're going to do in this class. And then car 2 against the ground or the earth was going 30. And because you're stationary, that is why you see them going 25 and 30, because you're standing on the earth, not moving. So we'll always pick a reference. We'll pick a spot. This is us. We'll pick a spot. We'll call it the origin, and then we'll measure everything. So the person standing here would be like our origin, and we would measure the cars moving by the origin because it's a stationary reference point. So the first thing we're going to do is we're going to define, if we're going to measure things, we need to define different types of measurements. So the first one we're going to define is called the displacement. And the displacement is the shortest distance between the final and initial positions. So you can imagine that you started here where the red dot is, as the arrow shows. This is where you start. And wherever you start, that's where you're going to mark your origin. So we'll say that we started here at our initial position is 0, 0. At some point later in time, we're over here at our final position. And it's going to turn out that the shortest distance is this red arrow, and this red arrow is our displacement, because the red arrow connects the initial here. This was our initial. It connects our initial and final points. And when we connect it with this displacement vector, it is independent of how the object gets there. We have no information of the path that it took. And so what happens is the path that the particle took to get from our initial, from here, which is our initial, to the final, it could have been this green squiggle. But what we know is that our displacement is actually something like this red vector and not the squiggle. But what we do know is most people think about this, and this is the distance. So the distance would be the path that you walk when you covered the green squiggle. And so the distance is measured along the path. So the green squiggle could be some long path. The displacement is the vector connecting the initial and the final. So when we talk about the displacement, what we're going to do is we're going to say that our initial is x1. This is our initial, and our final is x2. These initial can also be written, in the initial you may also see it. The initial can also be called like x0 or x0. That's a horrible. There, let's try this again. x0, x1. It's just usually or it can also be called xi for x initial. So those are the ones that you can see for the initial point. And your final point, the final point in this case, we call it x2, but it can be either x or xf for x final. So just so you know, there's different labeling systems that can be used. But for our introductory purposes, the displacement vector, which is the vector connecting these 2 points, that vector is defined as x2 minus x1. So it defines the difference, the displacement between those 2 points. Our initial x1 and our final x2 is defined as delta x. And this delta, that delta means the difference. So it's literally saying the difference in x is x2 minus x1. Now note that this displacement can be positive or negative. So when we start here with x1 equals to 0, let's say, because we're starting at the origin, and x2, let's say, is 3, this case then our delta x is going to be 3 minus 0, which would be 3 units. So we would displace 3 units. And since it's pointing to the right, it's positive. So in our standard convention methods, usually we call to the right positive, and to the left we call that negative. So you can imagine then how we would get a negative displacement. So if we start now at x1 equals 3, and we end up at x2, which is the origin, so it's like you went out to the store to get milk, and then you're going to turn around and walk back to your house, and you count your house as the origin. In this case then, our delta x is going to be 0 minus 3, which is negative 3. And so the negative tells us it's just to the left. It means that we traveled to the left, because we said if you move to the left, it's a negative. If you go to the right, it's positive. So that's how we can think about displacements. They can be positive or negative. It's just telling us the direction that we went. So let's take our displacements and talk about how quickly we make them. And so when we talk about a displacement or distance traveled in some amount of time, now we're going to be talking about what we call speeds or velocities. So the first thing we're going to define is called our average speed. And our average speed is going to be how far we traveled, which is our distance. It's going to be like the actual path. And we're going to take our distance, and so we start a stopwatch at time 1. We stop the stopwatch when we get to where we're going, and that's time 2. And then we have our actual path traveled. And so when we define the speed, it's going to be that distance we traveled, the green line, divided by the time it took us to get there. So we have some time at location 1. So we have this time up here at location 1. We stop our stopwatch when we get to location 2. We take the time as time 2 minus time 1. And notice that time will always be positive. You can never have a negative time, because you will always start, let's say time 1 is some number, time 2 is some number that's larger because time has passed. So remember, time is always positive. Time is always positive. And then our distance, by definition, our distance will always be a positive number. So we have our average speed is the total distance we traveled divided by the time, and that gives us our average speed, which will be a positive number because both distance and time are always positive. Now when we want to talk about our average velocity, this is going to be our displacement. So the velocity is going to be a vector because displacement is a vector as well. And so what's going to happen is we're going to have some initial time here. When we start here, we see we have some initial time at position 1 or x1, and then we have a new time 2 at position 2 or x2. So you started at one point, this is like point 1, and you end at point 2, and it takes you some time to get from position 1 to position 2. And what it's going to be is that our velocity, our average velocity, this should be average velocity. Our average velocity is our displacement divided by time. So it's x2 minus x1, so it's where you finish. So this is like where you finish minus where you start, and then it's divided by the time it takes you to get there, time 2 minus time 1. So what we see is our average velocity, because it's a vector, it can be positive or negative, and if it's positive, as we said before, that means you're moving to the right, and if it's negative, it means it's to the left. And so now note that velocity is a vector and the direction matters. So we have this average velocity is the difference in our positions divided by the difference in the times, and we can write this we said is because it's a difference, we can use our delta shorthand notation, and because this is a difference, we can use our shorthand notation again. Now what we need to do is we need to think about how we can think about the average velocity and displacement in time. So if you want to think about your displacement, how much you're going to displace, you could take your average velocity times the time that you applied it for. So you have if you knew your velocity and you multiplied it by the time that you had this average velocity, that would tell you how much you're going to displace. So that's why we have average time times velocity gives you your displacement. So you can think of it as two different ways. Either you can take your displacement and divide it by time to get your average velocity, or if you have some average velocity times your time, that'll give you the displacements you had during that time. And please keep remembering that velocity is a vector and the direction matters. So it tells us whether we're going to the right or to the left, and velocity tells us how quickly we're doing that. Now we use the word average, but we also have something called the instantaneous velocity. And the instantaneous velocity occurs as we take our delta t to get smaller and smaller. What happens is we look at the delta x during, so we're going to examine this delta x. We examine delta x during small delta t's. So as our delta t gets small, as it approaches near zero, we get what's called the instantaneous velocity. And what we can think about is your average velocity is like connecting these 2 points here, and as we shrink, so this is over some period in time. So here's like t1, and down over here is like t2. But as we make t1 and t2 almost on top of each other, t1, t2, so here we make t1 and t2 almost on top of each other, then we have the velocity at some point in time. And what you can think about for people that really enjoy math and are kind of like the math buffs, what that really is that's the velocity is really this black line which is tangent to the point, which is tangent to this weird curve here at that point, and that's the slope of the line. So if you plot position versus time and you take the slope of a line at the point, that gives you the velocity. And so the velocity is just your instantaneous velocity is your velocity at one point in time. You can think about it as when you're like driving your car, your instantaneous velocity is whenever you're looking down at the speedometer and reading your speed at that moment in time. That's your instantaneous velocity. So let's take a look at how we can calculate a velocity. So we start with we have some ball, and we know that our ball, we say that it starts at x equals 8.4 centimeters. So x1 equals 8.4 centimeters, and t1 is 3 seconds. So our ball is doing something, and it's going to, it looks like it's moving to the left because it starts at 8.4 and it's going to end up at 4.2. So our ball ends up over here at x2 equal to negative 4.2, and this is when the clock is reading 6.1 seconds. So to get our average v, we take delta x over delta t, and this is going to be negative 4.2 minus 8.4 divided by 6.1 minus 3, and this looks to be negative 12.6 divided by 3.1. And this is going to be something close to 4. And it's 4.06, which we could call 4.1, and that would be, the units are centimeters per second. So velocities, our average velocity for the ball during this trip is 4.1 centimeters per second. And notice that the units of velocity are distance divided by time. They tell us the rate at which our ball is changing its position. So every second that goes by, sorry, it should be negative. Every second that goes by, our ball moves 4.1 centimeters to the left. And that's what velocity tells us. It tells us how quickly we're changing our position, or the rate of which we change our position. Alright, so what we need to talk about next is acceleration. So if velocity is the rate at which we change our position, we should be able to change our velocity. So like, you can think of acceleration as if you're sitting at a stop sign and you then hit your gas, you've changed your speed or velocity. The acceleration is the rate at which you change that velocity. So if you have a good car, your car goes from 0 to 60 very quickly. You have a large acceleration. If you have a low acceleration, it takes you longer to go from 0 to 60 because the rate at which you change your velocity is smaller. And the big highlight is, try not to confuse accelerations and velocities. So velocity is how you change your position, acceleration is how you change velocity. So we're going to define our average, this would be average acceleration, as the change in velocity divided by time. So a change in velocity would mean we'd have a velocity 2 minus velocity 1. So we have velocity 2 minus velocity 1, time 2 over time 1. And whenever we have a change, we can use our little delta symbol. So we have delta v divided by delta t. So we have some velocity at some initial point, and then at some point later in time we have a different velocity, and in order to have a velocity change, you have to have an acceleration. And that's why we say here, accelerations cause our velocity to change. If you don't have an acceleration, your velocity doesn't change. So let's expand this out, and what we see is we see that A is equal to T2 minus T1 equals V2 minus V1. So if you think of this as at V1 as being at some initial point in time, what we see is V2 equals V1 plus your acceleration over some point period of time. So if you have some V1, if this is like your initial speed, initial velocity, your initial velocity, if you want to change your velocity to have some new velocity, you have to have some acceleration. So if A is 0, V2 equals V1, and you don't change your speed, whether you run your velocity, whether you want to have a positive velocity, like increase your velocity or decrease your velocity, you need to have an acceleration applied for some time to do that. So we have a negative. We also want to make sure we're going to give some definitions. So negative acceleration is an acceleration that's pointing to the left, and it's causing your system to have an increase in the velocity in the negative direction. So you can think of it as you're sitting here in your car, you're moving to the left, and you have an acceleration to the left. That's a negative acceleration. Now, if you want to have a positive acceleration, you have an acceleration to the right, and your velocity is to the right, so your acceleration is causing you to have a positive gain. Now, what we're going to define as a deceleration is if you have a positive velocity and you have an acceleration in the negative direction, then your cars or your system is decelerating because your acceleration points against your velocity. This would be like when you hit the brakes, your car slows down. And that's because we said already that V2 equals V1 plus A times your T2 minus T1. So if you started off at, so your new speed is going to be V2 15 minus 15 times T2 minus T1 minus T1. So the idea is that because this A is negative here, because we have this negative A, that negative A is going to cause our velocity to become smaller in time. And that's what a deceleration is. Our velocity becomes smaller in time. So, as an example here, using our system of the fact that V2 equals V1 plus A times T2 minus T1, let's take a look at what would happen to our car. So this is our conditions at t equals at point 1 when t equals 0. So this is like our initial conditions, initial. And let's say that we have this deceleration. We have this deceleration applied for a few seconds. So let's say we want to know the car's speed after we have this deceleration, or the acceleration's to the left and our velocity's to the right, and we want to say that what's our speed going to be like after the final, after we have T2 equal to 2. So let's take a look. Our final velocity, or V2, is going to be 15 minus 2 times T2, which is 2, minus T1, which is 0. So V2 should be 15 minus 4, which should be 11 meters per second. So after 2 seconds with our car experiencing this deceleration, our car would then be moving at 11 meters per second. Now we of course can also define an instantaneous acceleration, and the instantaneous acceleration would be when we take, this as we did before, is we take our delta t to be very small. So as instead of having t1 here and t2 over here, we bring t1 and t2 almost on top of each other, and that makes delta t very small, and then we approach the instantaneous acceleration. And of course, again, if we take a line tangent to the point, that would be the slope at that point, and that would be the slope of the velocity versus time curve, gives you the instantaneous acceleration. So what we want to do is we want to now look at some simple cases of average acceleration in one dimension. So if we have a sports car that accelerates from rest to 95 kilometers per hour in 4.3 seconds, what is this average acceleration? Well, first what we're going to need to do is take our 95 kilometers per hour and we need to convert it. So to convert this, we know that there is, in 1 kilometer, there's 1,000 meters. So this allows us to cancel our kilometers. And then we also know in 1 hour, there's 3,600 seconds. And this allows us to cancel our hour. So we can do our conversion. We take our 95 times 1,000 divided by 3,600, and we end up with 26.39 meters per second. So we know that this is going to be our V2 or V final. We know that T2 is going to be 4.3 seconds. We know that V1 equals 0 and T1 equals 0, because we say the sports car accelerates from rest. So rest means V1 equals 0 meters per second, and we'll assume that we're starting our stopwatch at T1 equals 0 seconds. So what kind of acceleration do we need to have this happen? So A is equal to V2 minus V1 over T2 minus T1. And this turns out to be 26.39 minus 0 over 4.3 minus 0. Dividing this out, we get an acceleration of 6.14 meters per second squared. So this was just a beginning look at the ideas of displacements, positions, and velocities.